Hi, I'm Jocelyn Matthews, and I run community at Pinecone. We are a vector database, and today we're going to talk about embeddings. The talk is not too vendor specific, it's more about the core concepts for developers. And let's just jump right into it. What are embeddings? Embeddings are numerical representations that capture the essential features and relationships of discrete objects like words or documents in a continuous vector space. So in other words, a vector is a long list of numbers, and each of those numbers is representing a dimension. Right here, we can see some data, and it could be of any kind, but typically text for the purposes of this discussion. And we're going to see that the data is being passed into an embedding model, which extracts features of the text and returns a list of numbers that represent those features. And there are many different embedding models you can use. They range from open source to closed source. But the key thing to understand about all of them is that embedding models convert our input data, like these queries, into lists of numbers, which are known as embeddings or vectors. There's a slight difference there, but they're used interchangeably a lot of times, that can be upserted and stored in a vector database. Importantly, these vectors capture the underlying meaning of the text or other data that was supplied to the model. So that means that embeddings are dynamic and context sensitive. They capture the essence of the data they represent, but they're influenced by the context in which they're used. So for example, embeddings that are trained on general text might not perform as well in specialized domains like medical or legal text, but you can find groups that are specialized to those domains. The adaptability is what makes them powerful, and this also means that you need to require careful consideration when you're choosing and training your models for specific applications. So you don't need to memorize this now, but I'm just going to throw out some terms that we'll be discussing. So a vector is a list of numbers that tell us about something, and we're all used to having things where we have numbers that tell us about something. So for example, RGB tells us how much red, green, or blue is in a color. And the word semantics means understanding the meaning of things and not just how they look or sound. So for a human example, you can think about if you have a big book of animal pictures, and I tell you, this is all of the animals that exist in the world, and I want you to only pull out pictures of animals that are pets. What would happen is that you wouldn't just look for that exact word. Instead, you'd understand that dogs, cats, hamsters, fish, some types are pets. But then you'd understand that maybe some other types of fish that you might have goldfish and you might have sharks. Goldfish might be a pet, but shark would not. And even though the word pet isn't written under their pictures, you're exercising semantic understanding where you're looking at the meaning and not just the words or images themselves. In computer terms, semantic search or understanding is when a computer can figure out what something means. And again, they're not just matching exact words or images. So it's like teaching a computer to think more like a human. Again, in real life, if you search for a car in a semantic search system, that might also show you results for automobile or vehicle. And that's because it understands those words are related in meaning, even though they look different. And then quickly, let's just talk about vectors. A vector is a mathematical structure with a size and a direction, and you may remember this from early school days. We can think of a vector as a point in space, and we can think of the direction as being an arrow that goes from the 0 point to that point in the vector space. As developers, you might find it easier to think of a vector as an array, which is containing numerical values. But what I want to draw your attention to is what happens when we get a bunch of vectors in the same space. So there's no way to put multiple vectors in the same space without some of them winding up closer together and some of them being further apart. We're going to see here in this diagram that some vectors can seem to cluster closer together and others are more sparsely distributed in the space. And building off of that, let's look at an example. So right here, we have 3 sentences at the top. And the first is, where's the Bank of England? The second is, where's the grassy bank? And the third is, how does a plane bank? And I've highlighted the word bank in blue 3 times. You can notice that even though the 3 queries are containing the same keyword bank, Because we pass the text through an embedding model to convert them to vectors representing their actual meaning, the resulting vectors, which are to the side with the arrows, are going to be spaced further apart. And that's because those three queries are talking about different things. The bank in the Bank of England is pretty far apart from how does a plane bank. And you can see that represented in the way that they're kind of shooting off in different directions and they're landing farther apart. Now, I'd like to draw your attention to the bottom of the slide where we have two more phrases. And the first is the bees decided to have a mutiny against their queen. The second is flying, stinging insects rebelled in opposition to the matriarch. And there's not a lot of repetition there, but you can see that the two vectors are landing quite close to each other. And that's because these bottom two sentences are saying the same thing, they're just using different words. So again, the embedding models are extracting the semantic meaning, and this is what is going to be really exciting when you go ahead and use it. In elementary school, most of us learned about homonyms, and homonyms are words that are pronounced the same and have different meanings. They have different roots, and they're unrelated senses of the same phonological word. And then if you've taken freshman linguistics, you might also have encountered the concept of polysemy. And polysemy refers to groupings of related but distinct senses of a single lexical term. So again, homonyms are the words that sound alike and have different meanings. And an example might be a vampire bat, which is an animal and flies in the air, versus a baseball bat, which is a piece of sports equipment. Like they're not related at all. And for polysemy, I have used as my demonstration different senses of the word point. And to better understand embeddings, let's visualize them in a 3D space. Now, this 3D space is by necessity a simplified representation. And we're going to see that each point represents a word, and the distance between points is indicating their semantic similarity. Once we have vectors, we can upsert them into a database, such as Pinecones, and when we send them into that vector database, it's going to work by grouping similar vectors close together and dissimilar vectors further apart. So right here, when we're looking at these embeddings in a high-dimensional vector space, we're seeing that the names of the days of the week are grouping closely together. And you can see that within that cluster, Friday, Saturday, and Sunday are also landing closer together, and Tuesday is further out. Now, if we had a homonym such as Sunday, the ice cream dessert, versus Sunday, the day of the week, that would actually be grouped further apart from the days of the week. So those were high level and a little bit conceptual. So what I'd like to do is take it from concept and go into some more concrete examples using everyday language and pictures, and then encourage you after we unpack those ideas to repack them yourself with the use of a thought exercise. And then we'll tie it back to the first few slides and you'll get the TLDR. We're going to look at word-to-vec arithmetic now, and this is the probably most common example that is used. And so some folks at a university went ahead and explored a mathematical property of this vector space, word-to-vec, which is that adding and subtracting vectors produces another vector in the same space. And this example is king minus man plus woman equals queen. And this is a very popular example. It's probably the first one most people encounter when they're talking about embeddings. And it has the virtue of working in multiple languages as well as being easy to remember. And when we add the vectors associated with king and woman and take away the vectors subtract man, we're going to get something that's equal to the vector associated with queen. And what's being described here is a gender relationship, but it actually doesn't have to be. So we could also substitute Paris minus France plus Poland equals Warsaw. And what's being expressed here, instead of a gender relationship, we are capturing the concept of a capital city. And we're going to go to another example now, but first here's the proximity slide again, and I'd like you to just look at it and see if you can remember it in your mind for the purposes of discussion. And we've talked about how vector databases work by grouping similar vectors close together and dissimilar ones further apart. Right Now we have this list of words, and I've just added another list. If we remember kids' puzzles that are connect the line from childhood, we're going to see that if we did this sort of puzzle here, that some words are going to be very straightforward and others are going to provoke hesitation. So in the first column, we have coffee, hospital, music, restaurant, and school. And I'd like you to ask yourself how the words on the right would show up if you wanted to put them into a visualization that looked like the days of the week one. And try to imagine the clusters the way that we had the cluster of Monday, Tuesday, Wednesday, and look at these words and think about which ones would be hard to envision and which ones would be easier inside those clusters. And then pick out a few words and try to think where they would be. So if you think about coffee, you're probably already done because I made that one really easy. Now, if you think about cup, that's obviously associated with coffee. Caffeine is associated with coffee. But I'd like you to consider on the lower right side of the screen the word exam. An exam is interesting because it could be associated with a hospital. Maybe you need a blood draw, maybe you need an x-ray, maybe it's a checkup. But exam could also credibly be associated with school. Maybe you're having finals, maybe you're sitting for an entry to college exam. And so the question is, where does exam go if we're making a diagram that looks like this days of the week one? And my question to you would be whether we could feasibly put all of the words that are currently showing on the screen into a 3D space, and would 3 dimensions be sufficient to hold it? And the answer is no. The reason for that is that the relationships between all of these words are complex, and they become even more complex the more you have. And so what's being required in order to represent them accurately is a high dimensional space. So we're going to go into a bit more of a thought experiment, and I'd like you to, we've packed and repacked, I would like you to think about how you would explain embeddings to someone else. So we've talked about word arithmetic, we've talked about word to vec, we've talked about king, queen, man, woman, and we've also just had a look at how that would be represented in a visual. And we're going to a color wheel now. And let's just say that you're living in green and you decide that you want to drive away from yellow. So if you go a couple of stops, you're going to end up in blue. So anytime that you start in a secondary color and drive that number of stops, you're going to wind up in a primary color. And you can exercise that same equation by starting in orange and going over 2 stops. You're going to end up in red. So green minus yellow equals blue, orange minus yellow equals red. That's always going to be how it works. So if we're talking about that and thinking about king, queen, man, woman, could we say that green is to blue as orange is to red? And my question to you is this a good way to understand and talk about the subject? And it's not quite. So there's a few things that are happening here. The first is that I moved this over from word arithmetic to a proportional analogy. So green is to blue as orange is to red. In each case, yes, we're subtracting yellow, but moving it from the word arithmetic to the analogy is not really logically consistent. The reason I'm using this as an example is because it's a common thing people do. So they just think man, woman, king, queen, and they've got it nailed. But in addition to that, which is not nothing, the analogy itself is really lacking. And I think this is where it gets interesting. So what it's attempting to do is to illustrate the relationships between colors, but it's falling short of capturing the complexity that you see in word embeddings. And there's a few reasons for that. So the first is the simplicity of relationships. And on a color wheel, the relationships between colors are very straightforward and they're linear. And importantly, they're also very symmetrical. So colors are easy to map. And the relationships are just based on really simple attributes like hue, saturation, brightness, and so forth. With word embeddings, what we're capturing has a lot more complexity and nuance. So word embeddings are considering context, they're considering usage, they're considering semantic meaning, and all of those things are a lot harder to represent when you're talking about something as simple as that. The second issue that we're running into is a lack of context. So the color analogy does not account for the context in which the words are used. It's a flat disk, it's 2D, and we already had seen in our previous slides that even 3D is way lower resolution than we need. So we went even lower than that, down from 3D to 2D. You're going to go 2 stops over, and that's just a fact. Secondary takes you to primary. But if you think back to the bank example, in those 3 examples, a bank can mean a financial institution like the Bank of England, it can mean the side of a river, or it could even be a verb such as banking a plane. And what's happening there is something very different. Colors don't change their meaning based on context in the same way as we saw in the bank example, but words actually do change their meaning based on context. And so this is making the analogy way less effective in illustrating how embeddings work. Now, if you're pushing back on what I just said and you're thinking colors have meanings and associations, that's true. And that's also why I picked the Billie Holiday graphic. So your spidey sense is tingling in the right direction, but I'm going to keep going. We're going to come back to this. But I want to talk about the third issue, which is really important that comes up, and that's dimensionality. And so green is to blue as orange is to red is really missing dimensionality. You remember I said that the color wheel is a 2D flat disk. That doesn't get us across the finish line. So a 3D example might be a box of crayons. So you can think that a box of crayons might have all of your colors. Similar colors when you first open the box are close together. Dissimilar colors are closer, further apart. But word embeddings aren't existing in 2D or 3D. They're existing in high dimensional spaces. And when I say high dimensional, I mean up in hundreds of dimensions. And that's what allows embeddings to capture the intricate relationships and the subtle differences between words. And so the color analogy just really oversimplifies this aspect. And for these reasons, it's just falling down. It's not conveying the richness. And we're going to keep moving. But I want to say that when we were working with this, we decided that we wanted to always check the vectors. And so we played around with different color term pairings, different start colors in different directions. And what we were looking for was the distance between blue and green. And then, for example, red and orange, and, hoping that we would see the evidence that would prove out what I'm talking about. But what happened was something really interesting. And what we found is that the distance between blue and green is incredibly similar to the distance between red and orange. But when we played around more, we found what's even closer to blue and green is the distance between red and purple. So why did we get purple and not orange? So red purple is closer to blue green than red orange is close to blue green, just to clarify what I'm saying. And the reason, it seems, is that red and purple are closer together semantically than red and orange. So in a color wheel, anytime you go 2 stops over from a secondary color, you're getting to a primary color. I've said that a couple of times. But in an embedding model where you're looking at things semantically, red and purple are closer together semantically than red and orange are. So blue and green are talked about in tandem together all the time. And I thought I picked that example off the top of my head, but I think now that I was actually influenced by the fact that blue and green are talked about in tandem all the time. So they're colors of nature, they're considered colors of harmony, they're colors of water, etc. And there's a lot of reasons for them to be yoked together ever more closely through the repetition of the ways that we talk about these colors. Red and purple versus red and orange are spoken about together and paired more frequently red and purple are paired together more frequently than red and orange. I want to be clear about what I'm saying. So if you think about examples that have to do with design, or makeup or fashion. Red and purple are used together more frequently than red and orange are. It's just less common. If you think about in terms of power, red and purple are spoken about together in terms of being power colors more frequently than red and orange. Red is the color of a power suit. Purple is the color of royalty. Orange is not a power color that I'm aware of, or at least it's not common. So what's happening is that it's yielding purple because the cosine distance and the direction calculations are resulting in purple being the closest match. So what is the TLDR? I'll tie this back to our initial slide because I read that through, but hopefully it resonates a little bit better now after this discussion. So what are embeddings? We've seen that embeddings are a long list of numbers. They're numerical representations, with each number representing a dimension in a high dimensional space. That's the first part. And those numerical representations capture the essential features and relationships of discrete objects. And we've seen that through the examples of days of the week and colors and so forth. And we've seen that we've looked at contextual meaning being the difference between a bank as a financial institution and bank as the side of a river. And we looked at semantic similarity, which is grouping similar concepts like king, queen in the context of royalty. And we've looked at complex relationships where we are understanding the nuanced differences like the exam in a school setting versus a hospital setting. So all of these essential features and relationships, we're at the second part of the bold print now, of the discrete objects, all get mapped together in a continuous vector space. And then we know that embedding models convert our input data into lists of numbers, which are known as embeddings or vectors. And these are upserted and stored in a vector database. And finally, we saw that vectors capture the underlying meaning of the text or other data that's supplied to your model. So the important thing you want to understand, they capture semantic meaning, and that this, importantly, allows for really efficient comparison of similarity. Your walkaway, things that are close together are similar, things that are far apart are dissimilar. And you might be wondering about some other key points. I'll just say quickly, they can represent various types of data. And if you'd like to get started with making some of your own embeddings, feel free to go ahead and check this QR code. I'm going to move over these quickly for purposes of time. There's Database API, Inference API, and Assistant API. I want to give a shout out to those. Feel free to reach out. This is my LinkedIn if you'd like to take a picture of it. And here is my email. Thank you so much for your time, and I've enjoyed these 25 minutes with you. Have a great day.